Okay, we'll get going here. Welcome. Thank you for taking the time to attend Cantana's Innovation Series. We have a great topic today, Agile Lakehouse, an iterative approach to enterprise data lakehouse deployment. I'm Greg Ingen, the president of Cantata, and I'm joined by my colleague, Dhruv Joshi, who's a senior manager in our data engineering practice. And Dhruv will take us through most of the content today. Just in the way of a brief introduction to Cantata, we're a Minneapolis-based consultancy specializing in digital transformation, which really means modernizing and sometimes migrating data infrastructure and technology for our client base. In addition to data engineering practice that you'll hear about today with this presentation, we also specialize in predictive analytics and specifically AI and machine learning model development, as well as application development. So we're excited that you're able to join us today, and thank you for your time, and I'll hand it over to Dhruv.
Thank you, Greg, and good morning to everybody. Welcome to today's webinar, and I'm excited to be here to talk about the Agile Data Lakehouse. Now, I'm not particularly sure about the audience, but if you're an ETL engineer, a data scientist, a business professional, or simply curious about the future of data architecture, I'm sure you'll find something useful with this presentation. So let's start with what we are going to talk about today. So we'll go to the next slide and show you the agenda. So one, we want to set up some sort of base around why we are going towards the Lakehouse architecture and what kind of problems we want to solve with this architecture. Second is how we've been through in terms of the whole industry, what have we experimented with and where we are in terms of Lakehouse and why Lakehouse is de facto standard. Third, we'll talk in detail about the Lakehouse architecture itself, how it is supported by technologies like Delta tables, right, and how different companies are approaching the Lakehouse architecture on their own platforms. Fourth is what we'll talk about Cantata's approach towards Lakehouse and how we try to orient itself in an agile manner, and that's why we're calling it Agile Lakehouse, a methodology which provides quick output to our customers so that they don't have to wait for a couple of weeks before we set up a Lakehouse and then provide some sort of analytics on top of it. So we'll talk about point number 4, which I think is the most important point in the whole thing, because from business owners, that is what they really want to know. So I'm just going to quickly talk about the problems that we're trying to solve in the next slide. Okay, so there are a couple of elephants in terms of when you talk about problems. And basically, I don't say elephant, but elephants because there are two things that we've been trying to solve in the last couple of years in the data industry with different architectures that we've experimented in the last 1 decade. So the first one is the big data problem. Now, the term big data was coined back in 1990s. And at that point of time, only a few companies had data which could be considered as big data. Anybody who had about 10 terabytes or 100 terabytes of data in that range was a big data company. Today, the world is very different. Today, everybody has multiple 1 terabyte hard disk drive, external hard disk drives, which stores the pictures of the family from different vacations. So every single one of us is producing data which can be qualified in the name of semi-big data. And a whole family or a couple of years online, we have generated enough data that could be qualified as big data in ourselves. So let's acknowledge the point that we're creating so much of data. In fact, let's look at the quote from Eric Schmidt, executive chairman at Google. He said famously a couple of years back, about a decade back, that there are 5 exabytes of information which was created since the dawn of civilization till 2003. But that's how much information that is now created every 2 days. And in today's time, almost every half a day. If you look at this graph here, it will show you a couple of things. It will show you how, and it's a logarithmic graph to the power of 100. The log base is $100 per terabyte. The cost of producing data or storing data, managing data or computing has gone down drastically over a period of time. In last 70 years, we've come to the point where a terabyte is nothing, right? And this has been aided by advancements in technologies, and that is one of the probably big reason why, because things are cheaper, we can produce more, we can store more, and we can think about things like data lakes or places where we can dump data continuously and keep pumping it over time and run big algorithms on top of this data, because compute has also gone down. So this technology aid is both a boon and a bane. It's a boon because we can do a lot more. A bane because it increases problem on technologies like data warehouses, which were not built for this kind of data boom. They really did not anticipate that we'll be operating in the margins of hundreds of terabyte on regular basis in almost a small company to a medium company range. They were created as server farmhouses which could operate for very big corporations in hundreds terabyte of range. So that's where data warehouses actually failed up with so much of data coming up. Now, let's talk a bit about why do we need to store so much data. So one thing that really comes to us that we could be one of those companies which are in the business of data. Now think companies like YouTube, Facebook, Twitter, Netflix, Wall Street Journal, company which stores currency conversion data for every day for every single currency, even digital currency like Fixer. So we could be a company, we could be in the business of producing consumer data, companies like these. Then you really need to store data for distribution or for even producing original content. The second thing is, like everybody else, you need your fix of BI. You need to identify trends in your corporation's data, extract the insight which can help you take the best decision for the business. BI is nothing. It's a general term for creating data-driven decisions so that you can actually do something really good about the business. You can make more profits maybe. The third is you need it for something exotic like machine learning. It's not exotic anymore with chat GPT breaking the ceiling now. Almost everybody's talking about large language models, how they can benefit from good AI. So you need this for machine learning. And because machine learning typically requires large amount of data for initial training, you need to have lots and lots of data in your storage. So these are primary three reasons. But I guess we should also address the other part that in last 2 decades, almost every other form of data, paper, your pictures, your movies, your cassettes, VHS, all of them have converged into digital format. So your pictures, movies, videos, storybooks even are now all digital. All the reports and journals in the offices and scientific institutions are now digital. Even the art is now digital, right? People are creating NFTs and selling them as digital art. So all of that is digital, and very soon we probably have, probably digital currency across the world, apart from bitcoins and the stuff. But they'll become the de facto standard for everything else. So if we are going to go towards digital, and we really need to store all of this. So that is the reason why we need to store so much of data. Now, when you start storing data, the traditional approach towards BI has been that you start with something, you start storing, you start analytics on top of it, and at certain point of time, you start sharing that data. That is when you realize that you are a part of a second problem, which is the data silo problem. So let's go with the definition. So yeah, and data silo can be called as an isolated repository which is not connected or unconnected to other data repositories and is unavailable for use by most users in the organization. Okay. Let's talk about typical scenario in a large multinational corporation. There are different departments. Each department has its own need for BI. Each department has its own need for data storage, and it has worked well. Now, we cannot anticipate all of the departments of this big corporation will follow the same standard. So typically, each team has its own IT team, a small set of people working in the IT for that particular department. Each team is producing large amount of data, which it understands and manages. Each team stores its own data in its own platform of choice. Each team maintains its own storage and application environments, which are used to monitor this data and archiving, partitioning, all of those things are happening at local level. The policies are not global. And over a period of time, this starts building up. Over a period of time, they start realizing that while they can utilize their data very efficiently, they cannot share this data with any other organization or collaborate very efficiently towards creating an organization-wide data warehouse. That's when they understand that they are now part of a data silo. Their data is in a silo and it cannot be easily shared with other people in the organization or the departments in the organization. One of the biggest problem that data silo presents is that some data that we may be collecting on a particular entity like a customer, we cannot club that customer data or augment the data with the customer data in which is part of a different silo. So even though as an organization we have data on the customer, but we cannot produce a total unified view of the customer, which hampers analytics, which hampers everything down the line. So as data starts growing, we start understanding we are part of silos. Now, the other problems, apart from this problem that there's in unconnected data, is that we lose the vision around data. We lose the veracity around the data. We don't know which silo is actually the source of truth, which silo contains bad information. So one of our database may say this particular customer has let's say we're collecting data about customer and we're a car service manufacturer. We already know this guy is a prior customer and we may say he has a Model S car. And the other silo may say he's just a prospect. He's never bought a car from us because that's what the data we collected in a particular survey from. Now we really don't know which of this is the real source of truth. So we, until the time we club them, both of departments will be operating under different assumptions. So that is one big problem with silo. There are others I can quickly list down. Uh, Data can be stale, out of date, or modified. It may be hard to connect the data between different silos. Other problems that we see are more political problems. People battle over the ownership of data. Every department wants this data to be stored in their particular format, and so that it eases their operations. And other department may talk about how they want to store it in a different format. Many times you would be simply storing this data in duplicate places into different silos, trying to interconnect via ETL processes, which all of this which are storage expensive as well as operation expensive. So bringing one data into two different silos from a third different silo means writing two different ETL jobs and then syncing them back would mean you're running many midnight ETL jobs which are totally unnecessary. And the last thing, and often there is an audit on data, and when you figure out that we are not doing a good job in maintaining the data, and data is actually not really good in any place. So those are some prominent problems. Now, to solve these two big problems with data silo and reducing large amount and storing large amount of big data, we continue our journey into Lakehouse. Now, we start with what the early solutions were. So one of the early solutions that emerged in 90s was data warehousing. Data warehousing was a good solution because it was preceded by a solution around reporting databases, the concept of OLTP and OLAP databases. And OLAP databases was basically just reporting databases where nightly jobs will take data from OLTP servers and store it and then store in a format which is more optimized for reporting. Data warehouses provided much better use with facts and dimensions, Kimball and Mon models, so that data can be processed by ETL pipelines and be available all the time for any sort of analytics on top of data. Also, it was able to bring data from different silos into a single place, which could be used as a single source of truth. And with trial and error over a period of time, you could actually establish which is the real source of truth and continue to use that forward. The initial version of data warehouses talked about the areas like data management, master data management, data governance, which laid down the foundation for what we know as data glossary, data catalogs today. We understand that we need to do a lot of metadata maintenance to actually figure out what is the usable data. So a typical initial early solution of data warehouse looked like this. You had your own operational data. You had data that you collected from a couple of different external sources. You will run an ETL pipeline like an SSIS, or if it's a cloud, some other pipeline like ADF. Bring this data into data warehouse, right? And then push the data out into different data marts. Each data mart would serve a particular department. This could be finance, this could be operation, this could be marketing, right? And this could be a sales data mart. And each of the data mart would be owned by a different department and they'll run analytics on top of them, which they really wanted to. So there are some limitations as well. As the data size started growing up, the typical on-premise data warehouse started becoming expensive because you could not really scale very well. Now, with the advent of cloud, where scaling was reduced to a problem, even cloud data warehouses are very expensive. You end up pushing more and more data without a good data archival policy or data deletion policy, your bill starts growing up, your cost of ownership starts growing up over a period of time. Many time when you create a data warehouse, you typically provision it for the peak load. So you understand that in 5 years, there will be a time when you have so much of data in your data warehouse and you still need to run your queries efficiently inside an hour or a couple of minutes for analytics. You always start with that particular peak load in mind. So that is one problem. You start over provision, you start overspending right from day one. Most of the data warehouses used a closed format, a proprietary format of particular organization. For example, Microsoft uses its own SQL Server based data warehouses where it is using its own proprietary format for storing into its SQL Server. If you were using a NoSQL solution, you probably are using something else. If you're using Postgres, you're using something else. So all of these formats were closed and proprietary, and data interchange was not very easy. You actually had to write a lot of different connectors to efficiently migrate data from one place to another. In fact, a lot of different problems and challenges in last 2 decades with data warehouse have been in converting data from one format to another. Trying to bring data from an Oracle into a SQL Server, you have to think about how you are converting those date types. So these kind of problems always result in a vendor lock-in. And let's also talk about another big problem. Remember, we talked about the big data problem where we talked about most of the other formats of information that converge into digital. The data warehouse here only solves the problem around things which are available as flat files, not as binary data or blob data. The data warehouse doesn't do any good job with unstructured data unless you can put a schema on top of data, unless you can convert it to one of the data type that it understands. It will not be able to store efficiently or provide for machine learning or any sort of analytics the unstructured data. So that or actually is one of the big limitation of data warehouse, that it doesn't play well with the unstructured data. And one of the recent studies has actually said that about 90% or more of data is unstructured data that organizations are collecting. People are collecting data from social media feeds, pictures, videos, all of the kind of stuff, which is actually 90% of data that is being produced these days. You are dealing with less and less reporting on article or numerical data, but more of unstructured data. So to solve the problem of growing unstructured data and the growing big data that you'll be collecting from different places, people started gravitating towards a new solution, a modern solution, which is called Data Lake. Data Lake was nothing but just an object storage, which had a layer of API built on top of it so that data can be accessed very easily as a file system. And because it was just an object store, it was pretty cheap. It was the earliest form of solution that was available on different clouds and was typically cloud-based. So a single repository for all enterprise data. The idea stemmed from the fact that let's not store data in our silos. We can put all our data in a single place, and that can be managed by ACLs, permissions on top of individual folders or containers inside the lake. And you can get the same sort of experience that you get on your file system, that you can browse through the data and structure it in different folders, all your data, and keep putting more and more data into the data lake because you could do so. The storage was very, very cheap. So even though you may end up with silos eventually on data lake, but those silos were very well segmented in terms of disk and partitions as well as the file structure on the lake. So even though they were silos, they were very easily approachable because you could easily give permissions to a department. They can access your data in a more managed format. And the best of all your unstructured data can be pushed into a single lake container. Whether you want to store images, whether you want to store videos, whether you want to store your CSVs, all of them can be pushed in there. And you could actually generate more and more copies of your data. For example, if you had a CSV file, which was the typical data that was generated from a particular transactional system, you can simply start storing that over there. And as part of batch processing, start cleaning that particular file and store it in a different format, or maybe for presented for analytics in a different other location. So you could stage the data, you can clean the data, and then you can refine it and put in all of these different files in different places, which are available for everybody else. So This solution kind of looked like this. You had your structured data, you had your unstructured data, all of them were migrated in ETL into a lake. And from lake, you could prepare data to multiple stages and transform them and keep copies of each stage of transformation as a separate file inside that lake, and keep putting more and more data and then present it for analytics and machine learning directly on top of this data. So one of the key things that you can actually see here is that this was more geared towards data science, because the data was in flat file, and a lot of different data science solutions were geared towards reading very, very large files from file system like data lake and do in-memory transformation using things like NumPy and Pandas and present it for machine learning algorithm. So this was quickly picked up by folks who were working on machine learning because they did not do well with the joining of different tables in data warehouse. The files were available, you could get a good preview, and you can start building your models right on top of it. Even basic analytics on top of R, Python, or even Power BI could be done on files present in data lake. So let's do a quick comparison between lake and warehouse. So data warehouse stores only structured data. A lake stores both structured and structured data. However, it is more suitable towards unstructured data and analyzing that, because a lot of structured data is typically organizations have their own warehouse, and they typically move from warehouse to lake their structured data and to run the analytics only on top of structured data from warehouse. Warehouses were expensive. Data lake was inexpensive because it was basically a storage solution and a pretty cheap solution. The data warehouse is targeted data analysts, people who want to run analytics on top of data. Later, lake was more towards for data scientists who want to run their models on large amount of data. Data warehouse delivers high performance. However, data lake performance is typically slow. Let's talk about this point a little bit more, because the performance was slow because lake is eventually just a storage. All the compute that you want to do will have to come as a separate stuff. You have to write your compute solution or run a Spark job or a Hive job or Hadoop job on top of this large amount of data, which is a separate solution altogether, which produces things. Now, typically, unless you are over provisioning for the compute, you will end up hitting performance bottlenecks because you have really, really large amount of data and different types of data and duplicate it, and you want to run those models. Your analysis from data warehouse will be faster because you have pre-stored and pre-computed and stored in a format which is easy to run analytics on. Data lake, however, is not geared for that. The warehouse data was a closed proprietary format of each OEM manufacturer, like Microsoft or like maybe Oracle. The lake was always in open format. File formats that were being used by Parquet, CSV, or JSON or XML, which were easier to manage and were very easily interconnectable or parsed by different people. Could actually open the file in an editor and actually look at the data and make sense out of it, rather than using a proprietary tool to watch over the data. Now, over this period of time, the industry quickly found a very hybrid solution. Let's have both data lake and a warehouse, because our problems are not being solved either by lake or warehouse. Warehouse is expensive and I cannot store non-structured data. Lake is cheap and I can store my non-structured data but does not give me quick analytics. So let me have both. So to get the best of both worlds, organizations started using both of these things together. This solution, this hybrid solution, actually gave superior durability and replication and low cost of data lakes, high as well as reliability in versioning of data warehouses. This, what we know in industry, the two-tier architecture is used to manage one solution for each of the use case, one for data scientists and one for the data analyst. This is how typically it looks like. You have data stored and fed into lake, all sorts of data, and then you utility data from lake into your data warehouse, into your real time. This could be the hot path and this could be the cold path of database, and consume as a data analyst into reports and BI solutions. As a data scientist, you could take the data from the lab, prep and validate using your Jupyter notebooks, and run your machine learning models or your data science solution on top of it, run your experiments on top of it. So both of these were actually taking data from data lake. So you had a data lake and then you had a data warehouse. So as you can understand, there are problems with this architecture as well. While it does provide best of the both worlds, it also combines the cost of both worlds. Your total cost of ownership went up because now you're maintaining both data lake as well as data mart. Your data reliability also takes a hit because The ETL jobs are not typically real time. They happen as a nightly job or a batch job. So that means that always a problem between the data that you see here or in the lake and the data that you see in the reports and behind the data mart. So it's very hard and expensive to actually keep the lake and the data warehouse in sync all the time. You always need continuous engineering and ETL data between the two systems because underlying data is unstructured data. If you get a new type of unstructured data, you have to write a new type of ETL pipeline to bring the data into a data warehouse. The pipelines had their own problems. They introduce a risk of failures, retries, partial ingestion, pipeline ran for a couple of hours, racked up a bill and then failed. So we need to rerun it. So all of these problems actually pose the risk on data reliability. You also wanted to figure out if you can do predictive analysis on top of data. And the leading machine learning frameworks did not do well with the data warehouses. So you actually had to train data on data which is available in Lake, or if you really want to access the data which is refined, you have to data backflow where from your real-time database and data marts, you have to restore data back into Lake so that this machine learning algorithms can actually access. There's no cross path directly from here to here. You have to bring it back down here and then take it back here. So that means that proprietary data formats of these particular data marts or data warehouses had to be converted back into an open source format before they can be fed into machine learning algorithms. And as soon as you did that, you lost a couple of things that data warehouse is famous for. You lost transactions, you lost indexing, you lost versioning. All of those things which are available and good features of data warehouse were lost. And finally, as I also said before, the cost of ownership is almost twice. You are paying for both the lake and data warehouse. You are paying for the ETL pipelines. You are paying to keep the data in proprietary format as well as in the open source format. Any sort of data migration is very, very hard. If you want to take data out from this particular lake plus warehouse into a different lake, you probably have to rebuilding everything and data migration is big. If you want to create a new data warehouse on top of this particular data lake, that itself is also expensive. So any kind of changes to this particular hybrid system, once it has been established as a system of use, it's very, very difficult. However, there was some merits to this approach because this showed the world that this is what all the organization needed. They wanted the best from the warehouse, which is basically asset properties, the transaction, the versioning, and the reliability of the data and prepared analytics. But they also wanted the cheap cost of data lake. They wanted to store non-structured data and they wanted to keep versions or incremental data keep coming in and they can keep processing without writing a lot of different ETL jobs. So the needs were clearly established, which bring us to what we call as a lakehouse architecture. This is a new modern solution, the data lakehouse. So Lakehouse, by definition, is a new open data management architecture. I'm emphasizing on this point, open data management. This is an open format. It is not something which is provided to a particular organization. Anybody can implement a data lakehouse if they follow the specifications. It combines flexibility and cost efficiency and scale of data lakes with the data management asset transaction of data warehouses. So it is trying to combine both of these things. Now, let's say, let's have a quick view about how does this look like. If I were to create a diagram and talk about what the solution looks like, this is how the solution looks like. You have a lake where eventually all data is going in and a metadata layer on top of it, which manages the need for all sort of people. For data analysts, where they are doing BI and streaming analytics, and data scientists, where they are running the data science experiments, machine learning models on top of this data. Particular layer, or what we call as a mapping layer, is something which is doing all the magic on top of lake and which is creating the lake house. But let's quickly talk about, even before we talk about what this kind of system is, let's talk about what does this mean. This means that you can keep getting the low cost storage of data lake. The data that you're going to store here is in a typical open format. The format of choice has been a favorite of almost every organization and every cloud vendor, and data scientists across the world has been Apache Parquet format. So that kind of has been a consistent rather than CSV or XML JSON. People are storing data in Parquet format on data lake, which is more of a columnar format, columnar table index format. So basically we're storing everything here in Parquet and in cheap manner on a data lake. And then this mapping layer on top of it actually provides all the properties of data warehouse, like access control. You can give fine granular access control on a particular folder. That means all the files in that particular folder are only accessible to a particular person at the file level, and in some frameworks and system, even at the columns inside the particular file or properties inside that particular file. You could import some sort of schema, like you have schemas and data warehouses and SQL servers and all the relational databases. You can enforce schema on top of the collection of these files. You could, get both the streaming data as well as batch data inside this particular data lake at any point of time, and the mapping layer would be able to manage that. You could have asset and transfer transaction control on top of this particular data via the mapping layer. You could run your data science and even create data as a products and export them into a data marketplace. So all of these things can be done very easily on top of this particular data lake by creating this lakehouse layer or mapping layer. Let's look at what does this lake layer actually look like. So this layer actually is a combination of three different services. It's called, you know, metadata caching and indexing layer. So basically what it does, it's on up every particular file in the lake, it has a lot of metadata on that particular file. When did this file change? What is the typical data preview of this particular file? What are the different other properties that we're going to maintain on this particular file? When was this last access? If we create a view on top of this file, can we cache that view? So all of those caching goes in. If you want to index this particular file or partition this particular file, the schema that is associated in this particular file. So all of that is stored in this particular mapping layer, which is supported by the metadata APIs. And on top of these metadata APIs, we built up two different types of APIs. One which supports a SQL, like a traditional T-SQL or PL/SQL kind of view inside a notebook or a data explorer for data analysts, which can actually create things just like they would do on a data warehouse. So they would never know that they are working with a data warehouse or we are actually working with a lake, which has file system behind the scenes. The SQL APIs will make them look like they are working on tables, text and dimensions. And declarative data frame APIs, which typically are built for Python and other type of usage for machine learning and data scientists, can run their experiments, write their code that they're familiar with using Jupyter Notebook, or run their applications built in Python directly on top of which use data frame like in pandas. So all of them are wrapper services on top of metadata APIs, which actually provide everything inside it. Yeah. Let's talk about what else we could get. So apart from these three things which I'm mentioning here, we also get the ATL service over here. So that means that we can start grabbing data from data lake into this metadata lake as soon as the data lands. There are triggers on top of it. You can create visualization directly on top of data that is over there. You could integrate with your favorite Git solution like GitHub or GitLab, or you could create your notebooks on top of this particular data independently, as well as you can decouple both the compute as well as storage resources like a good data lake solution. Data lake provides the cheap storage and all that compute that you need for SQL and data frame APIs or from metadata that can be provisioned in a cluster that you can run and manage at your own pace. If you want a very large cluster for doing large amount of work over a short period of time, you can upgrade your cluster independently and point it to this particular lake and start doing your work. If you want a small cluster, you can provision a small cluster and point it towards and just run SQL commands and utilities on top of it. So as I said, as a new modern solution, Data Lakehouse is just a management architecture. It's a set of specification, open specification of how to implement it. One of the implementation is done using Delta Lake, which has been done by a team at Databricks, where they've used the open source specification for Delta tables, Delta Lake, and they created a Delta Lake on top of actual lake, which could be your S3 bucket or your Azure Data Lake storage or Google Cloud storage. So Delta Lake serves as a mapping layer, which is boosted by a Delta engine. Okay? And this is being emerging as a format of choice across the industry for implementing a data lakehouse. What does Delta Lake actually promise? So like the promises in the specification for data lakehouse, data lake actually gives us asset transactions. It gives a table type interface on top of files, and we can get both the streaming and batch data in this particular file. It enforces schema on collection of these tables. It can create data versionings. It provides you time travel feature where you can actually go back and see what the data schema version was a couple of hours back, a couple of days back, what was data in there like. You can do upserts and deletes. So that was one of the big things, because this was an easy thing for people who are working in SQL data warehouses, that they can merge data in. Incoming data can be incrementally merged into via upserts and deletes into the existing data warehouse. To do that on a data lake solution is very, very difficult. You always get a new copy of the file, or you have multiple copies of the same file which may have the same overlapping data. You don't get a unified view. The Delta Lake provides you a uniform view using upserts and deletes, just like a table would. Behind the scenes, all data is in Parquet format, and the Delta Lake is designed to work with Apache Spark. So Spark is a language of choice, which is an MPP platform, and allows you to provision as many compute nodes as you want to quickly do your work. There is a Delta engine sitting on top of Delta Lake. This accelerates the performance of Delta Lake for SQL as well as data frame workloads or Databricks. So as we talked about, there was a SQL API and a data frame API that is managed by the Delta engine, and it actually accelerates performance on top of Data Lake. It can cache the results for each of the query, SQL query or data frame API lazy loaded queries. It can do dynamic file pruning for faster queries. It can do adaptive query execution and choose from runtime statistics the most efficient query execution plan, as well as it can natively vectorize the execution engine for fast processing. Now, for doing all of this, the Delta table that has been created by the inside the Delta Lake is actually a combination of two things: the actual Parquet file and a transaction log, which is also called a Delta log. At this point of time, I would quickly like to break out and show you something else. Let me quickly shift to a demo so that we see exactly what we're talking about. And I just realized that we are a little over time here, so I'll try to wrap this up quickly. Okay, can anybody give me a confirmation if they see browser on my screen and not the presentation?
Still on the presentation, Drew.
Okay, so we are here in a Databricks solution. I'll quickly show you a couple of things that I talked about. This Databricks solution implements data table Delta Lake by default. So let's quickly go through different views. So we have this Databricks solution, and we can see a tab for SQL, a tab for people who are data engineering who are going to actually create the ETL pipelines, a section for people who are data scientists who can run the experiments and run the models over here. So it's going to cater to all of these people. And you can create your workbooks. You can just quickly do workspace. This is my workspace here. You can see I'm connected to my Git repository here, and directly bring down code from that particular repository over here. Right. Then if you see here, I have my data over here. And just for this demo, I've also enabled DBFS browser. So if I just refresh this, it should start showing up over here. So this is where you are storing this is Databricks file storage. So this is just like your HDFS storage. You can see things that are stored as blob storage, actual blob storage right over here. This is a mount that I've created for a particular blob storage, which can be mapped over here, and I can store data and see data here. I'm going to quickly show you that for the purpose of this demo, I created a trial account and provisioned a trial compute cluster over here. This cluster is active. So let's go look at a particular notebook that I've been playing with. And when I say notebook, this is something that where you see typically data scientists working stuff. Now this first command is in Python Spark, PySpark, where I'm using file system to load this particular, look like the files in this particular storage data blob which I mounted. So if I see this here, I can also see this in my data explorer. This is my mount. This is a blob storage. These are all the folders and files inside it. You can also see them from here. So this provides a very nice little view of exploring your data lake and all the mounted repositories or mounted spaces on that particular data lake. I can read a particular file by using Spark, which I'm going to do now. Once I've read the file, I can look at the data inside the file by running this command, display command. It shows me a couple of things here. It shows me what the data looks like. There are 607 rows. It only took 0.543 seconds to read the entire file. Now I'm going to push this file as a delta table. So at this point of time, this file only exists as a blob object or a file object on prime storage in my data lake. And I'm going to use the delta lake technology to convert this into a delta table. So I'm going to write in delta format in an overwrite mode so that if it not exit, it will be overwritten into a delta table called employee delta. So I'm going to run this now. The job's running. And now we can just go here and look at this table here. So as you can see, I see the delta log table over here, and I also see the Parquet file which has been created over here for the employee data. So this shows me that I actually have a delta table. Now I can query this delta table using my standard SQL syntax by using this magic command %SQL inside Python and write my SQL query right afterwards. Select star from my table, and this is my table. I'm adding a limit of 10, so just the top 10 records. You can see how fast it is. It actually got it very quickly, data. And as you can see, this result for this particular cell also stored natively as a data frame in PySpark. So I'm going to skip a couple of things and just go down here. I'm going to read a file which contains 10 million records in a delta format from the Databricks dataset, sample dataset. So I'm going to start reading this file and let's see how much time does it take. These are 10 million records. They got loaded in 3.62 seconds. I'm going to partition this data by gender. So I can do apply partitioning. I'm going to partition all of this data by the gender and create a new delta table called people. Let me quickly show you how this looks like. As you can see, I have a delta log here and partitions with gender equal to F and gender equal to male, and the Parquet files are inside each of these particular partition. I can write queries on this, just like I would do on SQL Server or any other RDBMS tool. Write count queries. I can do group by, just like I would do on SQL. So anybody who's coming from a background of data analyst and is adept at using SQL day in, day out can actually quickly shift to this particular solution by loading a data into a delta table and then running a SQL just like this inside a notebook. Now, if notebook is something that you really don't want to do, Databricks has also come up with a SQL editor where you get the native experience of typical SQL editor. So I just need to create a SQL data, which is basically a compute cluster behind the scenes, which will be running the jobs. Can come in here. I can provision a particular cluster. Unfortunately, I don't have enough resources available in this trial account. Let's try a 2x small. Even that is small because 2x small requires 16 resources. I only have 10 CPUs, so I cannot do that. But if I've created a SQL data warehouse, I can quickly go in SQL editor, see my tables, all those delta tables as actual a table structure like you would see on a SQL editor, run my queries in typical SQL format, like a T-SQL or PSQL format over here, and run all my stored procedures, create table, those kind of things over here, like I would do in a SQL environment. I really don't need to worry about whether this is a file behind the scenes or whether this is a delta table behind the scenes. And for people who are machine learning enthusiasts, this has a similar kind of view where you can run your experiments and models. Now, just want to quickly show you, since we had 10 million records, let me run this query and see how fast this works. I'm going to sum by different genders. You remember we've done partitions on gender, so they should be pretty efficient. But I'm going to sum salary inside these particular files. I'm going to press now. We have our results inside 1.1 seconds. It's pretty fast because it is using MPP technology behind the scenes as part, so it is faster. And the speed is totally controlled by how many resources you have provisioned. So this brings best of the both worlds. It brings best of data warehousing as well like a SQL solution with all the transaction control, schemas, access control, who has permission on what particular table or view, as well as your ability to implement staging environments, final data marts, which can be or presentation layer, which is geared towards the actual end consumer. You can do all of that, as well as somebody could actually work with the actual files behind the scenes, Parquet files behind the scene, and run them into a data frame API and run the models and experiments on top of it. So I'll just quickly end my demo here because we have a little more ground to cover on the presentation. So I'm going to skip back to the meeting. So here we are, back to our slide. I just demonstrated what the SQL and Parquet format look like and how data was being stored. We'll quickly talk about the medallion architecture. So medallion architecture is just a fancy name which Databricks has introduced to the typical ETL pattern where you are loading data in incremental values. You have data which has been stored, landed into staging tables, where you have the raw data. Then you run transformations and imputations and all sort of data governance on top here to qualify data which can be actually merged together. And we should be able to create a view, which is the silver layer. And finally, you can take data from different silver layers and run aggregates on top of them after using join, which is typically called representation layer and data warehousing, and call that as a gold layer. So it helps incrementally, progressively improving data. This is some approach which is synonymous with data lake architecture. You store data or different copies of data into different partitions or different places where data has incremental and progressive good quality and structure and is more and more consumable in terms of analytics. So the medallion architecture is also part of your data lakehouse architecture. We also are trying to imbue a data mesh approach. Let's talk about this approach for a couple of minutes. Data mesh approach actually puts the onus on data owners to manage the data as a product. Right? It's a decentralized approach. In a typical ETL project or traditional data warehousing, you data analyst or database analyst would actually go and talk to different teams or different departments and ask them where the data is and how can I collect the data. Once the data has been collected, it's totally up to this ETL person or database analyst to figure out what that data is. And with some aid and support from the owners of the data or those departments, he's able to create facts in dimension and publish them in some sort of manner. And the end consumer, let's say the consumer is a top level marketing or top level management, they ask for certain KPIs. This person is responsible for creating those KPIs on top of the curated data. Now, there is a change in definition, and they want to know if they could actually change the definition by bringing another column from a particular source, which could help them refine or better than analytics and statistics. This person will actually have to go back to the owners of data and ask them, can I have this column as well? Can I also bring this data as well? And after clarifications and looking at the data in there, he will actually have to write new set of ETL pipelines or modify the current ETL pipelines and bring the data, bubble it up till the presentation layer. All of the onus or the work was on this database administrator. The data team was actually overloaded. The idea was the person who was working database team was not even a subject matter expert, was not actually going to use the data, and did not understand how the data originated actually, the data that he's collecting, what is the origin of data, and can he influence the origin of data to be collected in a better format. It would, however, have been better if data was treated as a product and the ownership lay with the person who was originating the data or the team which was part of data origination. So if they are going to collect data from marketing, marketing becomes the data originator, and any data that they provide should be their responsibility. They should be able to provide a good quality data which can be exported and used by other departments or a central team where from where they can be able to merge this data with other departments' data together. So the concept of data as a product and shifting the responsibility towards the owner in producing high quality data export is what the data mission approach actually completely encapsulates. So finally, we have something like this. If we combine the Delta Lakehouse with bronze, silver, and gold tables for different types of different qualities, and we add the data mesh approach, this is the diagram that we get. We get data from the source. It lands in the bronze table where we have live delta tables. That means they keep changing as more and more data gets in the batch or streaming method. We start cleaning them. There are jobs running on top of these tables where they are being pushed out into different new sets of delta tables, which are actual data mesh products, final level products after transformation curation into silver layer. And from there, they can be actually shared using the Databricks marketplace or shared internally into gold layer, where a good quality data mart can be created on top of data which has been obtained from different departments or data owners. And finally, this gold layer can be used either for machine learning or could be used for BI analytics. So this in total is the Lakehouse approach, which combines the best of both lake and data warehouse. Now we're going to quickly talk about a couple of things, how Contata has made changes over here. And this is the part I'm really excited about. At Contata, we understood that one thing that is missing in the Lakehouse approach is how do you execute it? Typical execution and the mindset around any of these technologies around big data is that once you give us data, we'll come back to you in 4 to 6 weeks with some initial products. And that's a long time frame, and it has been acceptable for a very long time. But today, people are impatient. People are used to instant fix, and they want to see results very quickly. And we can always talk about incremental quality and getting better with time, but something needs to be done since the data is there and has been landed. Something needs to be done on top of the data and can be quickly delivered as an output. So we've taken a agile stage approach. So like in a typical agile cycle where you have small sprints and you deliver incremental products of better value, starting with the minimal viable products and adding quality on top of it. We've taken a stage approach with Lakehouse-based data analytics. We have ensured that business involvement and value is actually delivered at each and every stage. The robustness, the speed, data governance, all of that increases incrementally. And there's a very small wait time before business starts getting a data product which they can use for analytics. We are also growing a data product catalog and data mesh architecture so that data that is provided is a first class data product or asset which can be used both internally and externally. And best of all, the lake could be in any cloud or even hybrid cloud. Overall, this is a development methodology. The Agile Data Lakehouse that Contata is pushing forward is a development methodology rather than a framework. There's already a framework with different lakehouse. Databricks has one. Microsoft is coming up with Fabric, and everybody's coming with their own particular lakehouses. So ours is a more of development methodology around these lakehouses, is leveraging any of these technologies, any of the cloud. Let's talk a bit about how we are able to do this. We are able to do this because we take a scenario where we have a client and the client is unable to share data till some agreements have been signed, but it's actually excited. The department which is waiting for these things to be signed up by and cleared by legal, it still wants to see what we can do with our data, still wants to browse its data. So we can have sessions uh, where we sit inside the closed premises of our client and we can talk about this data. We can create a working prototype on top of this by browsing through this data in the local environment and start delivering a product using any sort of analytics tool and try to map the business needs with the data that is available. Using data lakehouse, we can quickly push the data into a lake, a local lake, and then quickly start provisioning a small compute cluster to analyze this data. Once the quality and coverage has been assessed, we can directly push this into a small BI tool where we can run all sort of manipulations in a very agile manner and start creating the first set of analytics or maybe a data science experiment which can show some initial results. It takes some time before client gets the data access available to development partner like Contata. Once we have that access, we can start landing this data into a bronze layer where we will get the incremental files in a streaming process or batch process, and all of this will be pushed into lake as delta tables, and we'll start rebuilding what we built in the first layer or the first stage as a sample and expand that proof of concept very quickly into a quickly robust deliverable analytic solution. Now this may not have that quality that is expected of a final solution, but is still good and actually mirrors what was expected on a sample data in initial phase. We'll still do those transformations and cleaning, and we start analyzing more and more of these use cases. We start developing those governance tools which can be fitted into the silver layer data tool. And the silver layer data tool is actually the first class data product which can be used by different departments quickly or internally, or could be used to create combined analytics for other departments as a part of gold layer tool. So this is the agile approach for Agile Lakehouse. Agile is a term that Contata is adding as an additional value on top of existing Lakehouse frameworks and architecture. And I hope I've been able to convey the point across and push out something which is of imminent value to you. Thank you.
Thanks, Drew. Great presentation. That concludes our webinar for today. Thanks for joining, and look for our next webinar in our innovation series next month.